All right, let's learn the within subjects version of ANOVA, one-way analysis of variance. One IV within subjects. Repeated measures is a word you'll see used to describe within subjects designs because you get multiple measures from each participant, or you collect the DV from each participant multiple times. When do you use the one-way within ANOVA? One IV, three or more groups within subjects design. We got it. Null hypothesis. The IV has no impact on the DV in the population. The three or more population means are all perfectly identical. P-value less than 0.05 significance. The IV, we conclude that the IV has an impact on the DV in the population. Some people reject the null. So this is more complicated. My data lead me to believe the IV has a relationship to the DV in the population. Let go. I'm telling you, look at some psych journals. Let go of the way statisticians have taught you to talk about significant p-values. We don't write them up that way. We just use the word significant. We don't say we reject the null. Nobody writes that in their papers, y'all. Just let that go, all right? What we do is we write my IV appears to have an impact on the DV. We leave out the population bit in our writing, but you need to know that's our superpower. Greater than 0.05, you know nothing. Did the bad baby get on my research team again and run this experiment and just add a bunch of error to it? Maybe there was a difference, but my bad baby just made my data horrible, okay? Watch out for the bad baby. Effect size, eta squared, same thing. Proportion of the DV that was impacted by the IV. In this case, we're actually using partial eta squared, but it still has the same meaning. I will explain that, right? The eta squareds all have the same meaning. I will explain the partialness to it in a second once you understand what makes a within subjects design special. It removes individual differences. Okay. 0.01 is small. The IV caused 1% of the DV. 0.06 is medium. The IV caused 6% of the DV. 0.14 is large. The IV caused 6% of the DV. Let's do our data analysis. This was our data entry for between subjects designs. We're not going to do it this way, but I want you to see this, right? One row per participant. Each participant was in one condition and gave us one DV. So I have what condition they were in and what their score for reparation support was. I'm going to use the same data. I'm just going to assume that the first person in each condition is the same, the second is the same, and so forth. So now we enter our data one row per participant. So participant A, their reparation support when in the social justice history condition was 5. Their reparation support when in the no history condition was 1. Their reparation support when in the patriotic history condition was also 1. So I enter my data that way. This is how you do it, one row per participants. I'm going to click, well, this is what it looks like in Jamovi, right? I got 3 continuous variables and 1 ID, my participant ID. This is the same data. This is what it should look like, one row per participant. Each participant gives me 3 different DVs from each of the 3 conditions. Let's do our analysis. Analyses ANOVA, repeated measures ANOVA. Click those buttons. Then you get this part, and you have to type in a lot in that third box to the right. So you see my data. I'm going to call that the first box. You see my variable labels. I'm in the middle, right under repeated measures ANOVA. That's my second box. And over there in that repeated measures factors box, I just had to type out my design. So name your IV, name the 3 conditions. That's it. That's all you have to do. Then, now I zoom out a little bit, I got to put my DVs from that middle box to that right box underneath the first one, right? So we got repair social justice, repair no history, repair patriotic, with social justice, no history, and patriotic, right? Make sure your DV matches that little bold label on the right, okay? No big deal. If you keep looking down at the analysis, I click partial eta squared, not eta squared. I'll explain that in a moment. I click under estimated marginal means, click history in, click marginal means plots, marginal means tables. This one, you click standard error like always, and observe scores. So we have at the top, that's our omnibus test. You'll see like there's a component for, it says within subjects of facts and it says between subjects of facts. We are testing within subjects ANOVA. You can see that our p-value comes from that top chart. That middle chart is actually, if you look, it just is calculating the variance, sum squares, degrees of freedom, all that, for the individual participant effects. So these are the subjects effects. So, you know, sum squares subjects or sum squares participants or sum squared individuals. All this is the same variance calculation, but the data, what you use for the data is you average every participant's, all their 3 scores together, right? When you do that, you find out who, in this case, you find out individual differences and reparations like support. And so from that data, you can calculate a sum squares, that is sum squares of participants or individuals or subjects, depending on who you're talking to. Essentially, in the between subjects design, that was included in the error term. Remember, I'm using the same data, so that was in residuals. And now the important part here is it's removed from residuals. Remember that, right? The mathematical advantage that a within subjects design has is it can calculate individual differences on the DV and remove them from the error term. I'll go into that a little bit later on. So OP, right? OP of the OPP now, right? Outliers pattern. I'm looking at this data, looking at the first thing, looking for outliers. You know, I kind of noticed a cool pattern across all 3 conditions. There is some people who have strong support and some people have weak support for reparations across all 3 conditions. This spread is the largest in the no history condition. Am I seeing an outlier? Right? We in class we said, yes, there's nothing wrong with that. I mean, maybe not, but we definitely have some weird things going on in the data, particularly in the no history condition, right? If you look at that no history education condition, there's quite a bit of spread. At the very least, you can see a lack of equality of variances across the 3 conditions because there's a lot more spread in the middle condition. So there might be some problems with my data, and then I'm going to run non-parametric tests so that those quantitative problems aren't giving me p-values that are not accurate. The pattern's clear. Social justice history leads to more support for reparations than no history education, which leads to more support for reparations than a patriotic history teaching condition. P, OPP, our p-value is 0.05908, not significant, greater than 0.05. All right, that's so hard. Write it on your hand before the test, okay? Like, you don't have to, but, you know, definitely get used to that. P greater than 0.05, not 0.5, not 0.005. I know it's hard, but you'll get it. This is non-significant. My partial eta squared suggests that my IV is causing 50.7% of the DV. Yeah. So you're probably asking why partial eta squared instead of eta squared. So this analysis removes individual differences. Eta squared does not remove individual differences from the error term. So when I say, oh, the IV accounted for 50% of the DV, right? If I used eta squared, like, oh, the IV accounts for 50% of the DV, including the individual differences that I quantified and removed, right? So that's why we don't use eta squared, essentially. How does this work? You take each participant's score, you average it, you get individual differences in reparations, you calculate sum squares, degrees of freedom, mean squared, which is just variance from those data. The computers do it for us. We don't have to worry about it. If we used eta squared, we would be using a known source of error that we quantified and can remove, right? Known source of error, not unknown source of error. Like, we quantified the individual differences. We should remove them from our total our total part of the calculation. It's really total sum squares, but, we don't need to know that. And if I used eta squared, I wouldn't be representing my data in the most accurate way. I'd be including error in total and like quantified error in total. That's not good. So we don't do that. I think this is cool. On the left, you got your within subjects analysis. On the right, you got your between subjects analysis. Same data, right? I want to show you some similarities here. Number one, ignore FP ignore F and P for this whole discussion, all right? The sum squares of history education is 14.53, so is the sum squares of condition. That's the same. Degrees of freedom, that's the same too. You got 3 conditions minus 1 in both analyses. So the sum squares and degrees of freedom are the same within subjects and between subjects design for the IV source, okay? For the error source, you will notice that the sum squares for error and within subjects, that residual source is error, is smaller than the sum squares for the residual source in the between subjects design. We also notice an extra term, the variability due to individual differences. So that between subjects effects right there, that's saying, hey, differences across participants, differences between subjects. This residual calculation right there is just our calculation of individual differences like I described before. So the sum squares, degrees of freedom, mean squared are all based on those individual differences in overall reparation support. Now the important thing, I put it at the top, 14.133 plus 7.0667 equals 21.20. Why am I doing that? Look at your sum squares residual. In the within subjects effects column is 14.1333. Look at your sum squares for residual in the between subjects effects column over for the within subjects design is 7.0667. And now go over to the between subjects design and see that the residual sum squares is 21.200. This is all I'm going to cover about it to the math today, but the within subjects design is removing that quantified individual differences in preference of reparation, that is the sum squares of 7.0667, from the error term, because 21.200 is what we get in the error term when we don't remove individual differences. When we remove them, we get 14.1333. Now, if you look, the two F's are the same. That's a coincidence, and that's just because if you look at the mean squared error, you got 14.133 divided by 8. In the within subjects design, you got 21.20 divided by 12. Well, that's because we had 5 participants. The degrees of freedom due to the between subjects effect, of individuals, is 5 participants minus 1 is 4. That's always kind of like the degrees of freedom formula. Number of things minus 1. So you got 8 plus 4 is 12, right? You got a smaller error term, but you got less degrees of freedom. So there's a little bit of a trade-off there. 14 divided by 8 equals 1.766. That's a coincidence with 21.2 divided by 12 equaling the same number. All right. You're like, why are the p-values not the same? Because the F's are exactly the same. Well, that's because the degrees of freedom, when you have less degrees of freedom in that error term, it actually makes your p-values larger. And you'll also notice that the partial eta squared for the within subjects design is larger than the eta squared for the between subjects design, and that's because we removed individual differences from total. All right, so to get the 90% confidence interval of eta squared in the within subjects design, you got to click in our course website, you got to click the right option. Okay, this is a within subjects, the partial eta squared for within subjects F test, right? So I type in my F, degrees of freedom 1, condition 2, right? Degrees of freedom residual, that was 8. The other stuff underneath there is just computer code. I click run in command, and you see it just prints out my lower limit, my upper limit. My lower limit is technically negative. That's why it's showing up as NA, but you can just put it in has 0, right? That's actually the smallest, like it's less than, you can't have negative percentage, right? It's not going to give it to you. Right? So it's like, it just wouldn't make sense. So 0 to 66%, that's our 90% confidence interval. So the complete absence of an effect, less than small, small, medium, large, right? Our population effect could be anything from no effect whatsoever to a less than small effect to a small, medium, or large effect. There are no negative effects here because everything's squared. compared to t, right? T squared equals f. But yeah, yeah, that's basically it. Post-hocs are after the fact. Okay, let's talk post-hoc tests. In this case, the omnibus did not hit significanceville, so it's not going to stop in post-hoc town. Meaning you don't have to do post-hocs if you don't have a significant one-way ANOVA. You might be interested in it. You can click it. It doesn't matter. But let's say you wanted to run post-hocs. How do you do that? Well, you click the post-hoc box. You click the condition over. I clicked all of them, just like last time, just so you could see. Just so you could see what happens. And here, you know, you can see some stuff changes and stuff. We shouldn't be looking at this anyways. But you're like, oh, which one should I use? Just a reminder, right? If you made a priori hypotheses, use no correction. Totally fine with that. If you pre-registered, right? If you pre-registered before the fact, a priori, yeah, you can use no corrected test according to Jacob Cohen, who's like the most well-known quantitative psychologist ever. You should use Tukey when you have equal sample sizes. We do. Chaffee when you don't. You know, we don't, right? Like Bonferroni, you can Bonferroni anything. Home Bonferroni does Bonferroni better than Bonferroni. So you can home Bonferroni or Bonferroni anything. You know, I'm just, for my data, I'm a report Tukey. That's just it. It doesn't really matter at the end of the day. The write-up is the same as it was before, so I'm not going to go over it. You know, make your figure, add the bars, do word, insert shapes. And I inserted a text box as well to put NS and stars in there. So insert shapes, insert those brackets. You have other bracket choices. You can kind of see them in basic shapes. You got a whole bunch of brackets. The first two sets are two brackets together. You don't want to use those. The next four are all individual brackets. Use one of those and you'll be fine. We want to show which means are different in our post-hoc test, so I don't have to write it up, right? That's the whole point. I'm saving myself a lot of time not writing means and standard deviations and, you know, not writing up every single post-hoc test. The history of manipulation did not significantly impact support for reparations. See figure 1. Our F statistic with 2 and 8 degrees of freedom equals our F statistic of 4.11. P equals the 0.05908. Eta squared. Eta squared can max out at 1 as well, so you don't have to put the 0 in front of that either. 0.51 with the lower limit of 0 and the upper limit of 0.67. The population effect is between no effect at all and a large effect. With this study, we didn't really learn anything. Now, we wouldn't do a post-hoc test after the fact, so we wouldn't do that, but we would write it up the same way we did for between. I crossed it out and I didn't change any of the stats, but like you would present it the same way. What's my T? What's my degrees of freedom? What's that actual T statistic? What's my P value? What's my Cohen's D? What's my 95 CI of Cohen's D? You put the name of your test in there. You interpret that population effect. Remember, the red ones are for me. You would never put that in a paper. You would definitely probably talk about it in the discussion maybe, but ultimately at the end of the day, that's for me to make sure you understand how to interpret the data. Once you graduate from this class, you won't have to do that anymore, but there you go. Now, we do have assumptions of the within subjects ANOVA. They're very similar to the assumptions we had before. You don't need to memorize these. To run the non-parametric test is quite easy. Analysis ANOVA, repeated measures ANOVA, right? Here I got to throw all my measures all my DVs into the measures box in that second box, right? And then your output, which I hid some things in that box, is telling me my p-value is still non-significant. Honestly, what I was looking for here, what I'll tell you I was looking for if this was my data, is that a violation of assumptions hid a significant effect. So I was kind of hoping, right, if this were real data, I'd be hoping that that Friedman test would have been significant, right? That would have suggested that my lack of significance in the first round like in the parametric test, was due to a violation of assumptions. All right, so ANOVA, so analysis ANOVA, repeated measures ANOVA under the non-parametric test. So it's the Friedman test. That's how it works.